And now I'll do a very quick review of complex numbers and the most important features and how to use them. So just as a quick reminder, complex numbers are based around what we call an imaginary unit, and sometimes we call it I, which is the square root of -1, but we're going to be referring to it as J because we're talking about circuits and I is current for us. And what we usually have is X as a complex number will be written as A plus J of B. Okay, and this is what we call a rectangular form or sometimes a Cartesian form. And if you plot it on a real and imaginary numbers in here, what we get is, for example, this is the real axis, this is the imaginary axis, and what we get is a number that looks something similar to this. Okay, so this one here will be A, for example, which is the real number, and this one will be B, which is this is the real number, this is B, which is the imaginary number. So this is how we represent it in rectangular form. We have also learned in math that we can represent these complex numbers in an exponential form, and that exponential form is simply x equals r e to the j of theta. Okay, and that pretty much tells me, well, r will be the magnitude in here. This is basically the length of this piece in here, or line piece or line segment, and theta, okay, which is here, theta or phi, it's up to you, what do you want to refer to it. This is here. And also, so this one here, we used to call it exponential, or it's typically referred to it as exponential. And we can write exponential in actually a different format, which is what we call a polar coordinate, which are pretty much the same, it's just a different notation. So it's basically you put the magnitude and you put the phase, because you can technically represent the whole complex numbers with a magnitude and phase, and that should be enough. These two are equivalent. The only difference is we're not using a e to the j theta. That's what we're doing. So this one here is, we usually call them polar. I typically refer to polar and exponential interchangeably because for me they look exactly the same, but mathematically speaking they're referred to differently. And we're also taught, like, you can convert between the different formats in here that we see. For example, let's assume that what we're given is the following. We're given rectangular format, okay, and we were asked to basically convert it to polar or exponential. Okay, so I'm going to say let's convert it to polar. So how do we do this? Basically what we know is A and B, and what we're looking for is R and theta. How do we get these? Well, pretty straightforward. So the amplitude of the magnitude is equal to A squared plus B squared. And of course this is under the square root in here, okay? And the phase or phase angle, we typically refer to it as theta or phi. What we say is the inverse tangent of B divided by A, which is the imaginary number divided by the real number. So this is how you convert from rectangular to polar. Sometimes what we have is the opposite. What we do have, and let me just draw that in a different number or a different color, for example, we get the polar originally, or that's what we know, and what we're asked to do is let's represent it in rectangular. Okay, and it's simple to see it from the graph, by the way. So what we're interested in is A, and then interested in B, what we have is theta and R. Well, hopefully you got that. What I'm looking for is A and B. Well, A is simply R times cosine of theta, and B will be R times sine of theta. That's pretty straightforward. And in here, I'm showing you the most basic operations you can do with complex numbers. So if we have a couple of complex numbers, those are x1 and x2, and they have a1 and a2, b1 and b2, or r1, theta 1, r2, theta 2, and it's like polar and exponential format. We can add them, subtract them from each other, multiply them. So you can pause the video and just check these operations in here. But what I can tell you is the following. Adding and subtracting is easier in the rectangular form. However, multiplying and dividing is easier in the polar or exponential form. The same here, well, this is the reciprocal, or maybe the square root, they're easier in the exponential or polar format. And we also have what we call complex conjugate. Usually put like a star in here, and it's simply, if this is a positive, you just basically take the negative, or the opposite. If it was negative, it becomes positive in here. And of course, 1 divided by j is just simply negative j, and the reason why is because you can multiply both. You can multiply the numerator by j and the denominator by j, but we know j squared is just simply -1, so that's why we get negative j in here. All right, so these are the most basic operations. So I'll give you an example of how you can utilize these. For example, let's assume that I gave you a couple of numbers in polar format, and I told you 65 is the magnitude and 70 degree, this is the first number, and I want to add it to 123 as a magnitude, negative 35 degrees. Okay, and then I want the square root of that. So what we have to do is we have a few things in here. Typically, I would use a calculator to get these results. Any basic scientific calculator should be able to do this, but I'll just show you how to do these very in detail, just so that at least you should know how to do it by hand, just in case. So for example, I'm trying to add two numbers, and I think it's just easier to add them using rectangular format. So I'm basically going to convert the 65 to 70 degrees into its polar coordinate. Well, we know that the A is just simply 65 times cosine of 70 degrees. And then the B, which would J, and then B, which is basically 65 times the sine of 70 degrees. Okay, we compute these two numbers, and what we get is the following. Hopefully we get 22.23. This is an approximation, by the way, plus J 61.08. Similarly, you can convert the 123, negative 35 degrees, into its rectangular format, and you should be getting 100.76, negative 70.55J. So now you can take these two in here and you can add them. So the addition should be basically, if we add just 65 and 70 degrees plus 123 and negative 35 degrees, what we have is the following. We have to add these two in here, so we get 122 point something, or maybe 123. Okay, it's 122.99. And then here what we do is we add the b's, okay, and the b's is 61 and 70. Actually, this is negative in 70, so it's basically negative 9 something. So 9.47J. So this is the result of summing these. Now what we need to do is we need to take the square root of that. So the square root, according to this one here, it's easier to do it in the polar coordinate. Okay, so I'll convert that to a polar coordinate, and I can tell you, well, this one here is simply you have to take 122. Let me just do that here. 122.99 squared plus well, technically it's negative 9 to 0.47 to the square, but I'll know that the negative will go away under the square root in here, and this one here will be tangent negative 1, and that's negative 9.47 divided by 122.99. This basically converts it to its polar coordinates, okay, and hopefully we will get 123.35, and the angle would be negative 4.40 degrees. Of course, this is not the final answer we're looking for, because we have to take this the square root of that, because I have that here. So the final answer would be simply the square root of the magnitude, which is 123.35, and the angle will be negative 4.40 divided by 2. Okay, and that answer will be 1.11 and negative 2.2 degrees.